I'm Joe Aumentado. I'm from NIST in Boulder, Colorado. Today, I'm going to give you a brief spiel about my perspective as a research scientist who has been developing RF and microwave tools for efforts in superconducting quantum computing. If you know about NIST, you might associate us with metrology or the science of measurement, but this isn't all we do. The T in NIST stands for technology, and since we're part of the U.S. Department of Commerce, much of what we do is focused on developing different technologies that support U.S. industry. So as such, we have major research efforts in both basic and applied aspects of quantum information science, including communications, sensing, and computing. So I'm situated at the Boulder NIST campus in the Advanced Microwave Photonics group, where we pursue research in quantum computing, optomechanics, and supporting technologies like low noise parametric amplifiers and cryogenic RF microwave component characterization. This last part, characterization, it's one of the less glamorous parts of our research, but it is super important. In the diagram on the right, we have a cartoon of a typical control and measurement chain. And what you'll notice is that the thing we think of as being quantum, the part with the qubits, is actually a very, very small part of the system. The rest is comprised of familiar microwave components, cabling, attenuators, circulators, isolators, connectors, and amplifiers. Part of understanding the physics of the quantum devices that we measure is actually understanding what this environment does and how it affects the devices we measure. And so we have to understand all of that very precisely. So as part of our research, we have over the years refined tools to understand this microwave environment very well. So one of the interesting aspects of a typical microwave measurement setup in superconducting quantum computing research is that they're often we're using components that are not actually vetted for cryogenic operation. They're often just off-the-shelf components purchased from popular vendors. So there are a lot of things that can change when you place them in such an extreme environment: dielectric constant, loss tangent, things that can go superconducting, et cetera, just because they're getting cold. Because of this, you can't measure their microwave characteristics at room temperature and expect them to be the same at very low temperatures. So likewise, many devices like solid state and superconducting amplifiers only operate well at very low temperatures. But even simple things like measuring scattering parameters are difficult to do because of the extreme environment that we're placing them in. And so an example that I'm showing here, my group demonstrated several years ago now, methodology for measuring scattering parameters at 20 millikelvin using electromechanical switches and TRL standards at the base plate of a dilution refrigerator. So it's not too different from what happens inside a commercial VNA, but we've extended it to the extreme environment of a dilution refrigerator using measurement wiring that we usually use for quantum research. If you look up the paper we wrote on this, you'll see a simple example where we de-embedded the scattering parameters of a double junction circulator at 20 millikelvin. This is one of the workhorse components that we use for our measurements. So understanding its performance very well can inform how we structure our measurements and analysis. So as another example, everyone in our field relies on some sort of low noise cryogenic amplifier to do their measurements. This might be a cryogenic HEMT-based amplifier, maybe combined with a lower noise superconducting parametric amplifier. One of the most important performance metrics of these amplifiers is the amplifier added noise, or the noise figure. But measuring the noise figure in some of these amplifiers is exceedingly difficult, especially when we talk about parametric amplifiers that have extremely low noise figures. One of the things that we've worked on in our group is noise measurement methodology using tunnel junctions as a self-calibrated noise source. All the amplifier noise performance measurements that you can think of require a well-defined noise source at their core. And this fills that role very well, especially since it's extremely simple and can be operated in a cryogenic environment. Lastly, I wanted to touch on the fact that there are many other aspects of cryogenic operation that we often don't talk about in this environment, but that good characterization tools can inform. So you might imagine that maybe the robustness of a microwave device is an issue especially when you thermally cycle it from room temperature to low temperatures repeatedly. You might ask how various other material properties or microwave properties change at cryogenic temperatures. And you might even ask other higher order questions like how do different materials thermalize at millikelvin temperatures, and how can I do that better? So before I end, I wanted to point out various resources and references that if you're interested in learning more. With the QED-C, I helped author a report that details a lot of the topics that I've touched on here. especially in the context of scaling to larger cryogenic quantum computing systems. So it's a great resource. If you're a QED-C member and have access to this, I suggest you take a look. The other thing I might show you flash really quickly is just some references to some of the things that I've shown you here. I'm happy to say that, so the stuff on the left is stuff from my group. Some of it's kind of dated, but I'm pleased to say that in recent years, there's been a lot more work in the same vein by other groups around the world, and expect that to continue to grow. Let's see. The other thing is I should mention I'm at NIST. In addition to my group, there's a larger internally funded effort that aims to cover and expand on characterization. If you're interested in learning more, I have a URL over here. The point of contact is this guy, Dylan Williams. This effort is mostly aimed at developing in situ cryogenic wafer probing techniques for large scale quantum computing systems, but many of you might be interested. So finally, my group doesn't really focus on these topics exclusively. We are mostly basic research, but we are mostly interested in detailing the basic methodology for doing this kind of thing yourself. And we published we've written several papers on this topic. However, I understand that a lot of companies have expressed a need for accessing this kind of expertise, and if that sounds like you, I'm happy if you just reach out to me directly, and I can try to contact or connect you to other people either through the QED-C or at NIST or elsewhere in industry that might help you get started. So that's all I have. Thanks.